For distal femur,
Yes, 1045.
our feet, our toes in? Okay, because Goldie was
Uh-oh.
saying no on that.
You did that.
I did that.
Okay, everybody at home just got sick. That wasn't me.
Knee and above, okay.
We'll pick up today in chapter 5. And what we're going to do is we're going to define some of the components that we haven't talked about in the imaging system yet. And further describe what KVP and mass do and how we control the different components of KVP and the different aspects of mass, your MA and your time. What we're going to start with is just description of the systems. So our imaging systems can be described in really one of two different ways. One is by the energy that they produce. So the energy that they produce would be things like difference between mammography and diagnostic systems. Mammography certainly is diagnostic, but it's its own subspecialty, its own modality now. So in mammography, what are we looking for? What are we looking at?
Adipose tissue.
Adipose tissue, that's the only thing that we're looking at is adipose tissue, some ducting, and what we call microcalcifications, which are indications that the patient has a tumor. So what does KVP control? Voltage. And in the voltage, what does that control in our exposure? Quality, yeah, very good, you read ahead, right? Very good. The quality of the x-ray beam. Okay, so if we're talking about quality of the x-ray beam, what are we trying to accomplish in making an x-ray? What do we have to have in order to see the x-rays like what you can barely see over there because the lights are off? But what does the x-ray beam have to do in order to give us that? That's penetrate, right? So KVP controls penetration. Penetration is the quality of the x-ray beam. If I were to shoot a chest x-ray with 10 KVP, what kind of KVP do we use for chest x-ray? 100 to 120. If we're doing portables, you may go a little bit lower than that, but very high KVP, right? So if I were to do that same chest x-ray with 10 KVP, what do you suppose we would see? Not much, right? So an x-ray beam that doesn't penetrate, for our purposes, has no quality at all. So equate KVP with quality. The higher the KVP, the higher the beam quality. Doesn't necessarily mean the higher the x-ray quality, the x-ray image quality. So we'll get into that later on, but think of KVP as beam quality, and we'll talk about why here in a bit. So in mammography, we don't have to penetrate through as thick of tissues, because if you've ever had a mammogram, you know that they mash it down and they squish it really, really flat. It's very uncomfortable. So it's not going through a whole lot of tissue, right? So the penetration doesn't have to be as high in mammography as what it does in diagnostic x-rays. So your mammo unit's probably not going to go above about 35 kVp. Your diagnostic unit's probably not going to go above 150 kVp. So in a diagnostic range, what you've got are machines that even your diagnostic x-ray units will go sometimes as low as 25 kVp. You're never going to use that on anything. But they'll go up to 150 kVp, and you're probably never going to use that either. But that's your basic range of diagnostic x-ray energies. Whereas mammography is probably going to go more in the range of maybe 15, 20 kVp all the way up to no more than 50. So they can be identified by the energy that they produce. That's number one. And number two is their actual usage. So again, we've got mammo units, but we've also got radiography, fluoroscopy. Once in a while you may run across a machine that does tomography, and we'll talk about that. And some of your units do both radiography, or your rooms do both radiography and fluoroscopy. So with a radiography room, what you'll see, you go into clinicals tomorrow, and what you should see if you look up at the ceiling is you'll see rails, some embedded into the ceiling, or you go into the lab today, you'll see them. Some will be embedded into the ceiling, and they'll go the length of the room in one direction. They're not very far apart, but that's one set of rails. And then there's another set of rails that goes perpendicular to that. So there's two sets of rails mounted perpendicular to each other, and then you've got the tower with the x-ray tube. You're looking down from the ceiling. The x-ray tube will be underneath all this, and it rides on the second set of rails. So you got some stops here, some stops there, so you can't run it off the rails. Some stops here, some stops here. So you got wheels that run this set of rails just up and down the room this way, and you've got wheels that run your tower up and down the room in this dimension. So you can take that tower anywhere into the room, very flexible. In your fluoroscopy rooms, you got a totally different set of x-rays and image receptors. So inside of the table, which they call it a couch, sometimes they'll call it a bed, x-ray bed. Inside of the x-ray couch, or underneath the couch, inside of the table assembly, you've got a fluoro x-ray tube. So in your rooms, what you've got is, in a radiography room, just a diagnostic radiography room, what you've got is this setup here. But in what we call an RF room, that's radiography and fluoroscopy, what you'll have is two x-ray tubes. One's going to be in here, and you've got this one over here as well. So you've got one on the tower, and you got one inside the table. It's that great big thing that you manipulate whenever you're doing a fluoro case is actually the image intensifier. That's your image receptor, right? So inside the table, you've got another x-ray tube. And there's a lot of logistics that have to go into the construction of x-ray room and what everything needs to be made out of. So regardless of whether you're in just a plain radiography room or an RF room, what you're gonna have is an image receptor or a bucky inside of the table, right? So the bucky holds your image receptor. Your image receptor may be removable, like what we have in the lab, or it may be fixed in place so that it can't move, it can't come out at all. But if you're shooting into the table, we have to have certain characteristics. So let me back up a little bit. So we can have radiography rooms, we can have fluoroscopy rooms, or we can have RF rooms and then mammography. So we can identify them also by their usage, as their usage. All right, so regardless of whether we're doing radiography, fluoroscopy, or if we have an RF room, certain components have to be in place and made in a certain way. So if you've got the table and you've got an image receptor inside of the bucky, and we call that a Potter bucky diaphragm. And it's just named after the guys that invented it. The Potter bucky diaphragm is where you put your image receptor. So it's not the image receptor itself, but that's where the image receptor goes. But if the patient is here on top of the table, apparently a very tall patient hanging off the table, then our x-ray beam and our x-ray tube has, and we use x-ray tube above the patient, x-ray beam has to go through the patient and reach the image receptor. So what characteristics do you suppose that tabletop has to be made of? What's that? Radiolucent. It's got to be radiolucent. Remember, there's not radioparent, but there is radiolucent, and there's degrees of radiolucency. So certain things are pretty radiolucent. Wood you can see through, but it casts artifacts. Plastic you can see through, but it's not as radiolucent as carbon fiber. Another problem with plastic is that it has a tendency to cush. It has a tendency to bend. Your little disposable, we used to call them Tupperware, I don't know what you call them now, little disposable dishes, that you always lose the dish and keep the lid. You mash on those and they give very easily, right? So they used to make tabletops out of those, but what we had to have is a lot of bracing in place to make sure that, you know, the patient didn't sag on the table. So what we use now is carbon fiber. And carbon fiber is very rigid, and at the same time, it's very radiolucent. Have you ever seen a patient, this occurs after a patient's had possibly a broken neck, but certainly after a neck surgery, they wear what we call an external fixator. And an external fixator, I think we talked about that maybe in positioning last week. We're looking at the images, and I said it was kind of like an exoskeleton. They call it a halo. And what the halo is the patient has this vest-like thing on, and he's got this thing sticking into his head with these little pins that screw into his head, and then he's got rods, these little black rods that go from the vest all the way up to the head portion. That's what we call halo. Those black rods, they look and they sound like metal. If you took metal and you tapped on that rod, it would sound like metal. So it'd sound like a lot like, that's not a metal ring. It sounded a lot like that, but it's not metal. It's carbon fiber. Very rigid, but it's radiolucent. So if you ever have a patient with an external fixator, the bright metal portions are truly metal, and they're hard to see through, but the black portions, not the black portions with screws in them, but the black portions that are just the rods themselves are carbon fiber, and they absorb almost no x-rays, okay? So we have carbon fiber as a tabletop. That's number one, is it's gotta be radiolucent, so we've gotta be able to shoot through it. If it's not radiolucent, can we still shoot through it? Well, if it's at a lower rate of radiolucency than carbon fiber, can we still shoot through it? Yeah, absolutely we can, but the problem is that in order to get a good image, a good x-ray image, we have to have a certain amount of radiation to the image receptor. So if this thing's absorbing a lot of our x-rays, then we're gonna have to apply more x-rays in order to get the right amount of x-rays to the image receptor. So where are those x-rays going? Two places really. One is into the table itself, which is useless, but at the same time, to get that number through the table, that patient's gonna have to absorb a lot of x-rays, right? So the carbon fiber, it gives us a high degree of radiolucency, plus it is it's supposed to be an O, it looks like 9. Very high level of radiolucency, but it's still very rigid, so it's an ideal material for the tabletop. The other thing though is that knowing that nothing is radioparent. Even if we have carbon fiber, and let's say it's very thin in one place, but it's very thick in another place, and then very thick in another place, and then very thick in another place, then even though it's radiolucent, will the tabletop absorb more x-rays in these areas than those areas? The answer is yes, absolutely will. So it would cast an artifact on every x-ray that you shoot. So two characteristics of the tabletop we gotta have. One is that it's gotta be radiolucent, and the other is that even if it's radiolucent, we have to have uniform thickness so that we don't have those artifacts and have differences in density on our image receptor when we make our exposure, okay? So in fluoroscopy rooms, everything is reversed. You don't have an x-ray tube above the patient, you have an x-ray tube below the patient inside the table itself. So this is x-ray tube. Now, our Potter-Bucky diaphragm has some components in it that you don't want to x-ray if you're not intending to x-ray them. Okay, first off, if you pull the tray out and look at the tray itself, yeah, what's it made out of? Metal, right. So metal, is it carbon fiber? No. So is it easy to penetrate through? No. And you can't really see it from here, but that x-ray up there, when you pass by after we get done, what you'll see are a lot of wires, right? So it looks like you got these round circles going maybe around the patient's aorta or whatever. It's not the aorta, it's the sternum. So the patient had open heart surgery. Those wires are made out of metal. So since they're metal, they show up really well on x-rays. So we got this big hunk of metal holding our image receptor. We don't want to x-ray through that. So first off, this thing has to have one of two different characteristics. One is it's got to be able to move up and down the table, as you know, from one end to the other, so that when we're doing a fluoroscopy case, we can either get this thing out of the way. Let's say we're doing a MRI on the C-spine, we want to put that thing all the way down at the bottom of the table. If we're doing a barium swallow, bottom of the table. But if we're doing a lumbar puncture, we might want to put it at the top of the table, depending on, you know, exactly how the patient's oriented on the table. It's got to get out of the way, right? So that's number one. Number two is that over the patient, you got this great big apparatus called the image intensifier. And that is your image receptor. So your x-ray tube is going to shoot up through the patient into the image intensifier. So the image intensifier should be lined up with the x-ray tube at all times. Again, let me back up a little bit. One other possibility is to have what we call a fluoro through bucky, okay? So that metal bucky could have a great big hole in it, and it could stay lined up with the x-ray tube, okay? That's a possibility. You don't see that quite as much as what you would think you would. If you go to surgery and you do a cysto case where they don't do a whole lot of moving the patient on the table, you'll see that. But in most of your diagnostic departments, you don't. It's either going to be at the top of the table or at the bottom of the table whenever you're doing fluoro. So anyway, back to the image intensifier. This is a big, heavy piece of machinery that's motor driven. So if it's heavy, we've already talked about momentum, right? It's hard to get started and it's hard to get stopped, right? So if you've played with the fluoro unit at all, you know, the handle is what activates the motor. So you give it a little bit of a push in one direction and it takes off, right? So you've got to kind of pull it back in the opposite direction and get it to stop. So if it's big and it's heavy and it moves relatively quickly, one thing that you've got to get used to in your room setup is where you're going to put that, because it's got to be out of the way of the fluoro tower. So in most cases, whenever you're setting up a fluoro room, two things you need to do is plan where you're going to put the bucky and plan where you're going to put the x-ray tube, the overhead crane assembly x-ray tube. Put it somewhere out of the way, usually on the opposite side of the table at one end of the room, as far away from the table as possible, because if you've got that x-ray tube hanging down right here, well, let's say right here, you get that fluoro tower going, something's going to break. I guarantee you something's going to break. The handles are going to break off, something's going to snap. So make sure you get that out of the way somewhere, okay? But even still, we've got, whenever we make an exposure on a patient, the possible interactions in the patient, fundamentally we've got four, right? So what we're going to have is the x-rays are either going to go through the patient and interact with the image receptor and not touch anything, right? And that is what we call penetration. Some penetrated x-rays are going to interact. So they're going to hit something, they're going to go off in an unintended direction, and that is what we call scatter radiation. And there's two different types of scatter. There is what we generally think of scatter as that right there, and that is what we call Compton scatter radiation. It just goes towards the image receptor, but it's got a lot of power still, but it goes, well, it can go off really in any direction at all, the Compton scatter. So we got Compton that can go off in any direction. So it can go towards the image receptor and mess up your image. It could bounce back down into the table, or it could bounce straight out towards you, like that. That's where your occupational exposure comes from, is from Compton scatter. Not all scatter radiation is going to bounce towards you, but some will, and that's where your occupational exposure comes from. The other type is what we call classical scattering, or Thompson. And Thompson scatter is low voltage, low kilovoltage, And it just almost completely parallels our penetration. So we don't talk a whole lot about Thompson because it doesn't matter. It's a very small percentage of our overall interaction, and it's almost indistinguishable from penetration. So it adds some density. It almost doesn't matter, okay? And the other is photoelectric absorption. So it doesn't penetrate through the patient at all. Now, some of your Compton and Thompson scatter inside of the patient will become photoelectric absorption, not penetrate through the patient, okay? So not all the scatter that you create is gonna exit the patient, and it's important to understand that, but it's still scattered, right? It's just not scatter that's gonna mess up anything, and it's not gonna add to your occupational dose. So, you have 4 possible interactions, really 3 categories. It's either gonna penetrate, it's gonna stop, or it's gonna scatter. Your dose comes off of that scatter, specifically Compton. And I went all that way to describe this function of your table. You're in a room that does fluoroscopy, and most of your rooms, your general diagnostic rooms are gonna be RF rooms. You've got probably some ER rooms that are just radiography, but I don't know that I've ever worked with a room that is strictly fluoroscopy that wasn't a specialty room, like special procedures or something like that. So most of your rooms are gonna be RF rooms. So have you ever noticed that whenever you move the bucky, and you probably haven't because you know they've designed tables now to where it's pretty seamless, but whenever you move the bucky, obviously that bucky is taking up space, right? So if it travels up and down the table, it is taking up space. What you've got in the bucky, or attached to the bucky, is kind of a solid plate that travels with the bucky. You grab that bucky and you drag it down to the foot of the table, and what you're gonna see is you got a plate on both sides of it that kind of moves with it, right? You drag it up towards the head of the table and it moves with you that way as well. Some of your rooms don't have that. Most of your more modern rooms do, but some of your older rooms don't have that. What they've got is this thing that if you flip it down, you can see the bucky, but this whole area down through here is wide open. There's nothing there, okay? You can actually look inside of that hole. That's what we call a bucky slot. You can look inside that big hole and you can see the x-ray tube down in there, and you can see all the barium that's leaked out of, you know, off of the table down into, it's just nasty. But you can see it. So what they've got is this little flip up door, all right, and the flip up door covers that. Now the reason I point that out is because if we've got these interactions inside of the patient and they bounce off the patient, the photons bounce off the patient and Compton scatter, and they go down through that hole is right here. So what part of your anatomy is right here? It's your gonads, right? So your dose coming through that bucky slot can be relatively high to a portion of your body you don't want to be exposed to high levels of dose, right? So that thing that drags with the bucky whenever you move is what we call a bucky slot, or bucky slot cover. What does a bucky slot cover do? It covers a bucky slot, right? So it covers a bucky slot so that you don't get as much Compton radiation straight through the bucky slot right to your gonads, right? So you're still wearing your apron, so your dose shouldn't be all that high, but the bucky slot cover is intended to protect you from even more radiation exposure, okay? So bucky slot cover. The table, there are 2 different designs in the table, depending on what type of table you have. If you're just working off of a radiography room, like what we have down in the lab, you step on a little pedal and it unlocks. We described the detents, so we described the solenoids that unlock things in the last section. Remember talking about that? So you step on that, it activates the solenoids, and solenoids release the brakes so that you can move that pretty much anywhere that you want it to go, and it moves, you know, as quickly as you want to move it, and very easily. And that's what we call a floating tabletop. So floating tabletop are, they're specific to radiography units. I've never worked with a fluoro unit that had a floating tabletop. And here's why. Even though those solenoids keep it from moving, for the most part, they're not as strong as the solenoids in the tower. So sometimes you can lean up against the table and the tabletop will move. All right? So anybody done a barium swallow? Okay. How do you start with a patient in barium swallow? Well, not a modified barium swallow, but more like an esophagram. They're standing up, right? Is that what you said? It sounded like sitting up.
Scout first.
Yeah, very good. Scout first, and then you start with them standing up. So you're in a fluoro room, and what you've got to do when you get prepared for these, you got to make sure that you got a footboard on the table. So you put the footboard on the table and jerk on that thing just as hard as you can for just a little bit, because it's got to lock into place. And if you put it on and it doesn't lock into place, and then you stand the table up, but there's not enough weight on it for it to fall off, the patient steps on it, it's going to hurt them, right? It might fall on their opposite foot. If it's an older patient, they put enough weight on it, they're going to fall into the tower, bash their head. It's just going to be ugly, right? So put the foot on it and pull on it real hard to make sure it's locked into place good. But if we had these floating tabletops in fluoro rooms, and if the footboard was on good anyway, and the patient stepped on it, and they weighed enough between the footboard, the table, and their own body weight to move that floating tabletop, again, you're back to the patient might fall down and fall into the unit and hurt themselves, okay? You don't want that. So floating tabletops, the benefit of floating tabletop is ease of movement. You step on that pedal and you can drag it anywhere you want to very quickly. The other type though are motor driven, and that's a fluoroscopy unit, is usually motor driven. The motor driven gives you a little bit more precision in your movement. You know, you don't have to eyeball quite so much. You can just kind of bump the patient in different directions until you get them to where they need to be. But at the same time, they provide more stability for fluoro units, so that if you have to put the patient in a standing position, or has anybody done a cervical myelogram yet? No? Cervical myelogram, they inject a contrast and then they strap the patient's feet into that footboard and then put the patient's head, lower the patient's head. And depending on whether or not they've got a lot of compressed discs or whatever, they may tilt them up quite a bit. So again, can you imagine being on an x-ray table? They already stuck your spine, and then they take the x-ray table, your head is here, and you're hanging on the table, and the table's like that, and then it starts to move. That'd be bad, right? So, the motor-driven tables are in your fluoroscopy rooms to prevent that, or any of those other problems that I was talking about before. So tabletops can be floating, motor-driven. Floating are going to be your diagnostic, your radiography, and then your motor-driven will be your RF rooms. Okay? Any questions on that? So what else in fluoroscopy can you use to reduce your dose?
Distance.
What's that?
Distance.
Distance is a big one. Distance is good for you, but as far as the user of the unit goes, be it a PA, a doctor, a tech, gloves, gloves, so you got shielding. Have you ever seen anybody use the fluoro unit without that drape? You should have a drape over the front of it goes from the image intensifier, so that you can't even see the patient really.
I've never seen that.
You've never seen them use it? Yeah. Oh, that's brilliant. Just absolutely brilliant. Yeah, they should be using that. It's basically like a double layer lead apron that just hangs from a fluoro tower itself. So yeah, that's a big, thing of shielding right there that they should be using. Not using. So certainly, yeah, distance, and then what else did I tell you could do? Stand behind them, exactly. Let them take the bullet. Because again, how much are you getting paid?
No, it's not.
Not at all, right? How much are they getting paid? More than not at all, right? So stand behind somebody if you can. Just don't make it weird.
Just don't make it weird.
All right, so overhead crane, two sets of rails perpendicular to each other. Any questions on all that? Just the basic room setup. No? All right. So regardless of, if you've got a mammo unit, you've got a radiography unit, you got an RF unit, even a therapy unit, basically what you're going to have, you can break down into three sections. So what you've got is operator's console. Operator's console is the only portion that is always going to be in a place that you can get away from radiation exposure. So in a diagnostic room, fluoroscopic room, RF room, that's going to be outside the room. So it's behind the glass. It's still technically in the room, but it's not in the room. You know what I mean? It's not out in the area of exposure, but it's still in the x-ray room. So you got an x-ray room, and you got a table here, and your console is going to be back here. In a mammo room, if you've ever been in a mammo rooms are tiny. They're a little big. They're like a closet. And this is just a movable piece of glass, but the operator's console is still behind that glass and away from the exposure. So the operator's console is outside of the room, and then the other two portions, you got the console. Then you've got the x-ray tube. So you got an x-ray tube inside the room, obviously. And then you've got the book calls it the high voltage generator. And it's not really a generator, it generates high voltage, and that's why they call it a generator. The definition of a generator is something that generates electricity. It doesn't generate electricity, it manipulates electricity. So I know it's kind of splitting hairs, but I think it's important to understand why they're calling it a generator. You're generating high voltage from low voltage, but you're not really generating electricity, okay? That thing could be almost anywhere. In some of your rooms, it's going to be, in the room itself, sometimes halfway behind the control panel. Sometimes it'll be up in a false ceiling. Some of your systems are built to where it may be actually inside the tower itself, okay? So the difference between those three things is the console is where you control everything, the tube is where you make the exposures, and the high voltage generator system is just that. It's what creates that high voltage, okay? So from the console, we're going to do a lot of different things. Some aren't really described in the textbook real well, but we're going to talk about them pretty much in depth. So you've got creation of milliamperage. Overall mass, right? Because MA times time gives us our mass, but we control them separately. If you've ever set a set technique, you've seen that. You can select your MA, you can select your time, and both of those go into creation of mass. So we can select our MA. MA we're going to call intensity. And I struggled with this when I was a kid, when I was a student, because I always thought of an intense kid as being somebody, that was just full of energy, and it just sounded like a powerful thing. But the power is actually the X-ray, the KVP in the X-ray beam. Intensity just means numbers in this context. It's just the numbers. So mass, we talk about mass, what are the words there? Milliamps, right? Milliamps per second. So what did we say an amp was? Current is coulomb, 1 coulomb flowing through a circuit per second, right, is what an amp is. So, and that's just a measure of electrons. It's a number of electrons. It's a 6.3 times 10 to the 18th power, so a count of electrons. It's just numbers, is all mass is. So MA, our overall mass is our intensity, is our overall numbers of x-rays that we're going to create. But the MA specifically, what is MA? Well, it's our milliamperage. And again, it is numbers, but we don't get numbers in exposure until we get exposure time in seconds. So what does MA control? Besides numbers?
The number of electrons?
Number of electrons, right? So it's the number of electrons in the X-ray tube itself. What do you think that goes into?
Has to do with the cathode and the anode?
Okay, that's actually mass, okay? We don't get mass until we hit exposure, and then they actually travel across the tube. So when you press your prep button, what are the steps that, what takes place?
It starts boiling off.
What's that?
Boiling off when it starts.
Boiling off of electrons, exactly. So when you press prep, you're actually getting MA, you're not getting mass, okay? You got MA going, and what you're doing is you're rotating the anode, and at the same time, you're creating that space charge by boiling off the electrons. They call that hot thermionic emissions, right? All you're doing is heating up the filament. So you're crowding electrons together. You know, thermionic emissions, creation of space charge. That sounds real technical, right? Doesn't it? All you're doing is lighting a light bulb. You do the exact same thing when you turn on an incandescent light bulb. That's a light bulb with a filament. When you turn it on, the reason it glows is because you're getting thermionic emissions. You're creating space charge. That's all you're doing. So all you did was turn on a light bulb and you spun a little spinning thing. That's all you did whenever you hit the prep button. So what we've got are numbers of electrons crowded around and on the filament. Okay? So it's glowing red hot. It's just like a light bulb at that point. That's all you've got is a light bulb. So you create MA. If you increase your MA, the only thing that you're doing is you're putting more and more electrons there. If you decrease your MA, you're not heating it up quite as much. So really, MA, the only thing that it controls all by itself is the heating of the filament, nothing else at this point. At exposure, you actually apply the seconds and you send as many of the electrons across the tube as you want to come to the mass value you set. But at prep, the only thing that you're doing is this right here. That's it. Okay? So MA equals intensity, intensity equals numbers, number of electrons. As MA goes up, we get more heating of the filament. When we apply mass, we send more electrons across the tube to create X-rays. Okay? So how do we control that? Well, let's just circuit down at the bottom. What do we call it? Okay, the step-down transformer's there. So step-down transformer looks like that, right? But that is the filament circuit. Filament circuit is responsible for providing low voltage and amperage to the filament so that we can create X-rays. Before it gets to this, though, it goes through the MA selector. All right, so what do we call the auto transformer? What do we call it? A rheostat. Yeah, what is a rheostat?
Changes it up and down.
Changes it up and down. You can increase or decrease whatever you're using. Voltage, amperage, power, whatever. It turns it up and down. So this is MA selector. So your MA selector may go from, I don't know, maybe, I've worked on systems where you could select as low as 10 MA. You don't see those a whole lot. So, you know, maybe select 100 MA, 200 MA, 400 MA, 600, and 1200 MA. Okay? So, what are you doing there? You're choosing, right? So if you go from 400 to 1200, you turn it up, and if you go from 400 to 100, you turn it down. So what is that? It's a rheostat, right? So the auto transformer is not the only rheostat you have. That's a rheostat as well. In this case, it's an MA selector with the auto transformer. What are we selecting? KVP, right. So it's a rheostat, it's just adjusting different things. So in the low voltage circuit, we've got a rheostat. Comes out of the rheostat, goes into the step down transformer. Remember, we've got a primary side and a secondary side. What are we stepping down here? Voltage, right. We're stepping down voltage. And then it comes out of this and it goes into our filament. Now, why would we want low voltage at this point? What controls whether or not those electrons go across the tube?
Seconds.
That?
Seconds? Or
That controls how long they go across the tube. But what controls whether or not they do? When do we get exposure? What do we have to apply to make them jump? Okay, so you got prep, you make exposure, what makes them go? Huh? Electricity, yeah, it is electricity, KVP. Okay, they don't jump across until the voltage gets high enough. So if our imaging systems work on voltage ranges anywhere from, depending on the system, 110 to, actually, all the way up to 440 volts. Okay, 110 volts. If you got a raw wire, a bare wire, and you get close enough to it, you might get some voltage or some electricity jump away from the wire to get you. Maybe not. But you get up to 440 volts, and you will. All right? So the distance between the filament and the anode itself is not very far. Excuse me, it's not very far. So if we use 440 volts in our imaging system, there's a very real possibility we're going to get electrons flow across the tube before we're ready for them to go. We don't want that to happen. So what we want, especially if we get a lot of electrons crowded around that, so what we have, or what we want in the filament before we're ready to apply kilovoltage, is very low volts. So we're talking about 15 to 30 volts, very low voltage, okay? So for context, you know, the electricity in the wall, 110, 120 volts. Those little bitty batteries, square batteries, that's 9 volts. So twice that, you know, so very, very low voltage. The electricity is not going to jump off of 15 volts to travel from cathode to anode, okay? So what we want in the filament is set amperage to heat this up so that we get thermionic emissions, creation of space charge, but we don't want those electrons to jump across the tube until we're ready for them to do so, until we hit the exposure button. At that point, we apply the high voltage, the kilovoltage, so that they'll travel across. So our filament actually works off a very low voltage before we're ready for it to go, okay? So, that's your low voltage circuit. Now, when we select our MA, what we're doing is we're manipulating this rheostat, okay? So we manipulate the rheostat, we set our MA, and it goes into the step-down transformer, so it gives us very low voltage. So that's one thing that you select, is your MA. That is your MA selector. Okay? So, we're going to just keep a select. We're going to keep a tab of what all we're talking about here. All right, so where do we control our KVP? At the other rheostat, which we call the auto transformer. Right, so auto transformer is here. An auto transformer, both of these work off of, actually all three of them really work off of the transformer law. And the transformer law says that the voltage change is going to be directly proportional to the difference or the ratio of turns on the primary side versus the secondary side of any kind of transformer. Okay, so the auto transformer, it's a rheostat. You can turn it up, turn it down. So the contacts on the primary side are relatively fixed. So what we're doing when we adjust KVP is that, let's say we've fed this thing 100, make it easy again, 100 volts. Then if we spread them out and we have 10 on the primary side and 11 on the secondary side, then what is our voltage going to do? Is it going to increase or decrease since I have more turns on the secondary side than what I have on the primary side? It's going to increase our voltage. Our amperage decreases. Amperage doesn't matter at this point. We've already taken care of amperage. We're not dealing with amperage up here. We've already dealt with that down there. So it's going to increase. Our turns ratio on the primary side is 10, secondary side is 11, so I can change it to 110 volts. I can change it more than that. What you can, about the extent to which you can change in the auto transformer, is about 2 times or half. So you may be able to go up to 200 volts all the way down to 100 volts. And that's the key, or all the way down to 50 volts, rather. And that's the key, is voltage. We have kilovoltage. Are we dealing with kilovoltage right here? No, we're not. We're dealing with voltage in an anticipation of it eventually becoming kilovoltage. We select our kilovoltage here. Okay, this is our KVP selector. So whenever you select your KVP, what you're actually doing is you're selecting the turns on the secondary side of your auto transformer. So you feed it 100 volts and you need to make an exposure, 50 kVp. Then what you might do is squeeze this down to where you have half of the turns on the secondary side than what you had on the primary side. So if you had half, again, these didn't change. The only thing that you did was squeeze those in. So you have half here compared to what you have there. So what is your voltage change? It's 50, right? So we got 50 volts. But how is that going to read on your control panel if this is our KVP selector? So what do you set? You're doing a hand, finger, let's say. What's your KVP that you set? In this case, 50, right? So are you actually setting 50 kVp? Not really. You're setting 50 volts, right? So that whenever you make your exposure, what comes in here is 100, and what goes out of there is 50. So why do we call it KVP? We'll call it KVP because after it comes out of that, what's it going to go into? Step up transformer. So how did this thing work? You could turn it up, turn it down, right? You could have more turns on the secondary side than what you had on the primary side. You could have fewer turns on the secondary side than what you had on the primary side. Can you do that over here? No, it's always going to be the same. So if your turns ratio is 1 to 1,000 and you feed this 50 volts, then what am I going to have over there? 50,000 volts, which is 50 kilovolts, right. So, does it matter that we're only reading 50 volts here? As long as this is right, then it's gonna give us exactly what we want over there. But when you're setting your voltage, what we're actually setting is voltage in anticipation of it becoming kilovoltage. So it is our KVP selector, but it's only giving us 50 volts. Why don't we run it through this first? Well, if 440 volts is going to create a spark, if you put two things close enough together, do you not think 50,000 volts would? Absolutely. Okay, so dangerous to work with at kilovoltage rates. You don't want to do that, right? You don't want to be in charge of the machine and pushing buttons that's giving you kilovoltage. You want to deal with low voltage. So, in as much as we can, we put everything on the primary side of the step-up transformer so that we're dealing with low voltage instead of high voltage. There are some things that have to be on the high voltage side, like the X-ray tube, has to be on the secondary side in the high voltage section, but everything that we can put in the low voltage section, we're going to put in the low voltage section. All right, so that's two things. We've got MA, and I want to change that to MA selection, KVP selection. KVP selection is by adjusting the contacts on the secondary side of the auto transformer, right? MA selection is in the filament circuit before it gets to the step down transformer. Okay, so we've got MA selection, we've got KVP selection. Now, we don't get mass until we send the electrons across the tube. Okay, so you walk into the room, you've positioned everything, you're doing a finger, you got the patient squared away, you mash the prep button, and what you get is rotation of the anode. The rotation of the anode is for protection of the X-ray tube. It spreads out the heat. Instead of concentrating the heat in just a little bitty area, it spreads it out over a much larger area so that it extends tube life. So you rotate the anode, you create the space charge, which is fermionic emissions, right? But you don't have tube current until you mash the secondary portion of that button, or you push the second button. That's when you energize this entire upper portion so the electrons travel across the tube. All right? So if you increase your KVP, let's say from 50 kVp to 100 kVp, what you're actually doing is you're accelerating the electrons across the tube faster. Okay, this becomes much more positive, this becomes much more negative. Opposites attract, they go across the tube faster. Okay, once they hit and they make X-rays, a very low rate, but once they make X-rays, the speed is all the same. You're going to run into questions at some point, probably already have, that ask you about the speed of the electrons versus the speed of the photons. Speed of the electrons changes according to the KVP you have set. Increase your KVP, the electrons travel faster. Increase your KVP, the photons travel all at the same speed because they're electromagnetic radiation, they travel at the speed of light, regardless of what the KVP level is, okay? So don't trip up on that. All right. So, also, in your control panel, you've got two different filaments, okay? You got two different filaments. You got a big filament and a little filament. And how you select those are with buttons that look like this. You've got two different buttons. One is a big square inside of a square, and one is a small square inside of a square. Okay? And what those are your filament selectors. So small square means small filament, big square means big filament. And what those control is the stream of electrons as they travel across the tube. So if you select the big one, then you're going to have a wide stream of electrons go across the tube. If you select the small one, you're going to have a small stream of electrons go across the tube. We're going to demonstrate this later in the semester, and Trina's probably gonna walk through it as well. But that's what you use to control sharpness of recorded detail, okay? Again, looking at the chest x-ray. You've got certain detail that you wanna see there. You wanna see the lung markings, you wanna see the edge of the ribs, but you got big anatomy there, right? So how important is it to see just the finest little bitty piece of anatomy on that x-ray? Not very, you know? I mean, we don't want to miss a diagnosis, but in as much as we need to see trabecular markings, what are we looking at there?
The lungs.
The lungs, right. Do we need to see trabecular marking? Probably not. So do we need real high detail?
No.
No. KUB. Can you pick out anything on a KUB yet?
No.
No, no, probably not. You will eventually, but right now, you can see spine, pelvis, and maybe some gas patterns, and that's about it, right? Everything else everything looks alike. Do you need to see extremely high detail on that? No. Okay, so back to mammo. What are you looking at in mammo? Adipose tissue, but inside that adipose tissue, what you're looking at is ducting, and what did I say was the indication of tumor?
The hardness.
The hardness, that's what you can palpate, but what you can see is what they call microcalcifications. Microcalcifications is exactly what it sounds like. So take your pen, pencil, and just as quickly as you can, dot it on the page. Okay, how big is that? Okay, now you put that over that chest x-ray, and how likely would you be to see it? Not very good, right? So in mammo, what we need is extremely high resolution. We need high resolution in the x-ray tube, we need high resolution in the image receptor, we need high resolution in the image display. But where that starts is, you know, it doesn't matter what the image display looks like if we didn't record a sharp image. So in mammo, what we're going to use is a tiny little bitty focal spot. So the filament's going to be extremely small to pick up those microcalcifications. If we use a diagnostic type filament in mammography, we're going to miss diagnoses. That's why it is that mammo is developed into its own entity now, is because we could miss a lot of diagnoses with x-ray tubes that we use. Okay, so the smaller that filament size, the smaller the focal spot. The smaller the focal spot, the higher the resolution. But it comes at a cost. You put all these electrons that I've drawn here on that little bitty filament right there, then I've taken all those hot ions, and I put it on a filament that doesn't have room for all those, right? So it doesn't have room for all those ions. Does it have room for all that heat? Probably not. So if I put all that heat on that little bitty filament, what am I going to do with that filament? Burn it up. Burn it up, right? So what I'm going to use that for is big exposures. Where I'm not really interested in seeing extremely high detail. What I'm going to use this for is for detail. So we've got focal spot selection as well. All right, so we've got MA, but we've also got to get to mass at some point. So we're going to camp probably for the rest of the time on timers. We've got a lot of different types of timers. The timer circuit, I already said that this is over here, and your KVP selection is on low voltage side for safety, right? I said everything that we can put on low voltage side, we're going to put on low voltage side. So our timer circuit is also going to be on the low voltage side. And you'll usually see it drawn on the upper portion in between the auto transformer and high voltage transformer. Okay, so when we make exposures, we already heated up the filament to the as hot as we want it to be, right? We make our exposure, if it's as hot as we want it to be, and the amperage that's going through it is set where we want it, and we make our exposure, then at any given point, those electrons traveling across the tube, we should be able to kind of count them and make an estimation of exactly how many electrons we sent across the tube. Keeping in mind that what we're dealing with is a tremendous number of electrons, right? Because again, it's, 6.3 times 10 to the 18th power, right? So it's a ridiculous number of electrons, and even if we're dealing with MA, and even at a low mass value, that's still a lot of electrons, right? So when I say a rough estimate, it's a rough estimate, but it's really pretty close to a good estimate. Our timers can actually be inaccurate to, I think it's within plus or minus 10%, okay? So it's an estimate, but it's really a pretty close estimate. So our timer circuit's going to be there. So we heat up the filament to where we want it to be. We set a specific time for that number of electrons to travel across the tube. And at the end of the time that we set, it terminates the exposure. So what kills your exposure is actually your timer circuit. Now, you got a lot of different ways to select a timer, or a couple of different ways anyway. So we got time selection. Some are going to require you to set your time, so you set a technique, you're doing a hand, you're going to set your KVP, you're going to set your MA, you're going to set your time. Even if it's on a system that does it all for you, you're still doing all that through the system itself. So setting KVP, MA, and time. Whenever you're phototiming though, you got a totally different set of circumstances going on, all right? You're still activating the timer circuit. Whenever you make your exposure, pay attention in clinicals, make your exposure, and look at your readout. And what you'll see is your KVP, and it'll give you an overall mass. So since it's giving you an overall mass, it's giving you MA, and it's giving you time, right? So you could calculate what your actual time is by dividing your mass by your MA to give you exactly what your exposure time was, but it's really pretty irrelevant exactly what it was. Just know that it happened. And how your phototimers work, I'll change boards, is your phototimers are nothing but basically a Geiger counter. It's a radiation detector. And whenever you get to clinicals, what you need to do is take a look at your wall bucky. You can't see it on the table bucky, but you can see it on a wall bucky. And what you'll see is either squares or circles like that. At least like that. Sometimes you'll see two more down here. And those are representative of your phototimers, okay? So your phototimers are just radiation detectors, and when you make an exposure, you set up your tube, your system, and let's say you push the button that says chest X-ray. Well, what do you want to see on chest X-ray? It's lungs. Primarily, you're looking at lungs, right? So if we just limit this down to 2 or to 3, and we're most interested in seeing lungs, which ones of these would most represent where your lungs would be on the image? The top two, right. So, again, I wouldn't recommend, you spend a whole lot of time studying your configuration whenever you get to clinicals and you're actually taking a patient, but get in the room and play with your machine. And what you'll see in a lot of cases is you can figure out, the photocells and the photocell arrangement whenever you're selecting different exams. So if you're shooting chest X-ray, chances are what you're going to have are these two energized and that one not. If you're shooting KUB, in a lot of cases, it's going to be the same thing. If you're shooting a T-spine or an L-spine, chances are those are not going to be energized, but that one is, because that's where your spine should be on your image, right? So what these things are is basically a counter for radiation exposure. That's all they are. So you make an exposure, and these things have a preset amount of radiation that they should receive. And once they do receive, you're gonna send a signal over to the timer circuit to discontinue the exposure. Remember, your timer circuit is what kills the exposure. That's what triggers the exposure to stop. So, let's say you're taking a chest X-ray on a patient. Let's say your machine is set, and understand that these are just numbers I'm putting out there. The machine, let's say, is set for your exposure timers to terminate the exposures when they receive 5 MR. 5 MR. Okay? They function independently, but at the same time in concert with each other. Okay, so they average out, but they're individual exposures. So let's say the patient's got a clear chest, they don't have any kind of condition, and we make an exposure and position the patient properly, then what's gonna happen is when these things receive 5 MR, they're gonna send a signal over to the timer circuit to kill the exposure. So now let's say we've got a patient, and we're doing a chest X-ray as the next patient, and your first patient was hyposthenic, so thin. Your next patient is hypersthenic, okay? So your machine doesn't have any kind of a setting for different patient sizes, but you've gone from hyposthenic patient to a hypersthenic patient. Can these see the patient and determine that you've got a hypersthenic patient versus asthenic patient or a hyposthenic patient? No. These things don't have a camera on them, they can't see. Okay? So we make an exposure on the hypersthenic patient. What do these things want? 5. Right. But I've got a thicker patient as opposed to a thinner patient. So what's going to happen with the thicker patient versus the thinner patient? If our MA is set, our KVP is set, what's going to change?
Timer.
The time. So these become your exposure timers. That's why they are what's the second part of that? Photogenic, well, they're photogenic, phototimers. Photocells, phototimers, that's what we call them as phototimers, is because they're going to terminate the exposure based on just what they're preset to terminate the exposure for. Okay? So if you've got a larger patient, a bigger patient, you shouldn't have to adjust anything. If you're shooting chest X-rays with 120 kVp, that's enough to get through anybody. Okay, so if you're shooting chest X-rays with 120 kVp and you get a hypersthenic patient versus an asthenic patient, what should you do with your KVP? Well, nothing. What are you going to have to do for these? Well, nothing. What's going to happen is with the asthenic patient, these are going to shut off quicker. They're going to send a signal over to the timer circuit to terminate the exposure faster than if you've got a hypersthenic patient. So applying that, what if we've got a patient, we had a healthy patient the first time, and our next patient has a massive pleural effusion. One whole lung is obliterated. Same thing, exactly. What's going to happen? It's going to terminate sooner. Now we go from that patient to a pediatric patient, a little bitty patient. If they're that little, we're going to make some other changes. But let's say a 12-year-old. What are these going to want?
5.
The same thing. So it's just going to terminate sooner. Okay. The only thing these things do is measure the amount of radiation coming through the patient. It's preset to give you a decent density based on the exam type that you're shooting, so that if you've got patients of different size or different anatomy or different pathologies, these things should adjust. That adjustment may be that this one goes up to 6 and this one goes, remains at 5 because this patient's got some sort of pathology over here. So it increases the time to terminate your exposure whenever you've got the proper amount. Now, can you override these? Yeah, you can. You absolutely can. So you got other buttons. We'll say cell selection. You got other buttons on your machine. Again, go into clinicals tomorrow and take a look. And what you'll see is one button that has a normal. One button might have a -1 One button might have a -2, one button may have a -3, and then you've got another button on top that has +1, +2, and +3, okay? Those are basically recalibration buttons for this, okay? So if you need an increase in exposure for whatever reason, we're gonna get into spines, right? And what you'll see in spines is that different body builds are going to require increase in exposure for certain things. Like sometimes it's hard to see through somebody who's got a thin waist and wide hips. It's hard to see the L5S1 joint space, okay? So what we may have to do is increase the density to that. So what we would do is maybe hit it with a +2, and a +2 might tell these things it doesn't really want 5 MR. And if you're doing a L5S1 spot, then it's gonna tell this one specifically, because you're not gonna have those energized, but it's gonna tell that one, I might want 7 MR. Okay? So that's how you can manipulate exposure whenever you're phototiming, is with the +1, +2 densities. You can also do it by changing your cell selection. You know, if you were back to the chest X-ray, if you were shooting a chest X-ray on a patient, you wanted to increase the exposure for whatever reason. So normally you would use the outer tube, right? But if you wanted to increase the exposure, where's the center one gonna be? Straight over the heart, straight over the spine. So is it gonna take that one longer to get to 5? Absolutely, absolutely. So you can manipulate your exposure by manipulating cell selection as well, but the easiest way to do it is to go with those. So cell selection plus the density selection as well. Density, exposure, selection. Okay? We're out of time, but we've got some other things that we're gonna identify as well, and we'll work on those on Friday. Any questions? Let me bring this back over here and readjust that, because they missed the plus and minuses and all that. All right, then we'll pick up there on Friday.